GUIs, nothing to do with image editing, animation, or any of those things. What I want to start talking about a little bit is efficiency and how to, well, not write code exactly, but how to design algorithms or processes that are efficient. So we'll start where most computer science courses start in this curricula, start in this thing, and those are the dual problems of searching and sorting. So, yep.
Can you do an example of multi-threading?
Not today, but possibly. Multi-threading in Python is not perfect because it's not really part of the language. But in Java, it's actually part of the language. And our last 2 weeks of this course will be in Java, which will put you guys ahead, or at least nowhere behind the people who are taking the processing section of the course. So, right, because next semester you're all taking a course on programming in Java. So it's best if we have some brief introduction to that. So maybe I can talk about threading at that point. Okay, so let's look at the problem we want to solve, and let's go with so suppose someone gives us well, let's say that it's a list of numbers, which we also call an array, and they ask us to search in that list for, well, for a particular value. So we should be clear exactly what it means to search and what we want. So let's do this. So someone gives us this list or array A, and we want to, and some value x, and what we want to do is find the smallest value in A that is greater than or equal to x. Okay? Is that clear what that means? Yeah. So if we think about the elements of A, well, since they're numbers, we can just think of them as being points on the real line. Looks like this. And someone's giving us a value x, and according to our comment, we're supposed to find the smallest value that in A that is greater than or equal to x. So in that case, this is a value that's greater than or equal to x. This is a value greater than or equal to x. All of these are, and this is the smallest one. So this is the thing we should be finding. Okay. So this comment isn't completely precise, because what does it mean to find it? Yeah, but so what does it, well, I guess the question is, what does it mean to, well, to locate it or to find it in A? Should tell us the, well, we don't want to return all of them, we just want to return one, but you have to report it in some way. So you could tell you, I could tell you the value, but what else could I tell you that's even more useful than that?
How many times it's there, or all the numbers that are listed. Yeah.
A little more, yeah. Yeah.
The index of that number?
Yeah, so you could return the index of that value in A. Because that gives you the value. You can always just look at it, and it also tells you where it is if you want to change it or delete it or remove it or what. Yep.
But see, if we're using a set, we're using a list, isn't that going to mean that that value is possibly within that list multiple times?
Yeah. So
We'll have to tell it all of them.
we'll return the index of some value that's equal to the minimum, and that'll be determined, I don't know, somehow by the way the code works exactly. So let's say, more precisely, we're going to return the index of the smallest value in A that is greater than or equal to x. Is that still completely defined, this function? There's some implicit assumption here.
That it's there.
Well, that there's, so let's return the index of, return an index of, so that'll say we'll return 1 even though there may be more than 1. Yep.
That it actually exists.
That it actually exists. So when doesn't it exist?
If there's no number greater than x.
Yeah.
Then it equals x.
So for example, if this is my x over here, well, there's nothing in the set. So we'd better fix that up if such an element exists, and return, well, let's just return the length of A otherwise. So the length of A is not a valid index into A because the indices only go from 0 up to the length of A minus 1. So that'll be a clue to someone calling this that that the value we're looking for is not there. Okay. So how do we do this? Yep.
Turn A into a set first. Stop it's faster to search through A.
Well, sets are faster for searching, but they're faster for a different kind of searching. So sets are fast for testing if some particular value is in there.
Can we order it?
So we could order A, which is something we should do if we're going to do these queries a lot. So we could sort A, and then probably we could do this faster, and we'll do that shortly. But I mean, suppose this is a one-shot thing, and someone just gives us A and X. So then it's not really worth sorting A or doing something big to A, because if they're only going to ask this question once, it doesn't matter.
Shouldn't we have to sort it first, otherwise it's going to be really slow? So we have to do something with it to make it more efficient.
Well, if A is really, really big, then sorting it is going to take a really, really long time as well. So if we're only going to ask this question once, then it doesn't pay to sort it. It'll take longer to sort it than to just find the answer we're looking for. So how do we solve this problem? Nothing, don't worry about efficiency now. The first solution you think of is actually the most efficient you can have without any extra assumptions. Yeah.
For x and a, just find if you just take every value that's greater than x, then after that you just search through those and then you replace it. You make like another variable y, and then like if that y equals this, and then if it's less than whatever you found but greater than x, then it can be.
Okay.
You just replace that variable with that number.
Okay. So somehow we want to keep track of, we want to search through the elements in A, look at all of them. So we'll do it for y and A. So y will take on all the values in A. And every time we find a value, there's two things we want to check. If it's bigger than or equal to x, and if it is smaller than the best value we've found so far. So let's say our index so far will be, maybe we'll set it to, well, I don't know, well, let's set the index to the length of A. So we haven't found anything yet. And now we say if y is greater than or equal to x, then we want to do something.
Couldn't we do and?
Yeah, we can do and. If y is greater than or equal to x, and what?
Less than I.
And y is less than what? I? Well, I is going to be an index. So it's not I we want. Less than what?
Well, we need to take out a variable.
Why?
Because we need to make it save it somewhere. So we need like some random variable. That way.
Well, if we save I, if we save the index of the value we're looking for, then we also have the value we're looking for, right? It's just A at I. So if y is bigger than or equal to x, and y is smaller than A at I, then what do we want to do?
Add it into the
Yeah, now we want to save the index again, right?
random variable.
So this is a problem because we're not actually iterating over indices, so let's rework this. We don't want to go over the elements of A, we actually want to go over the indices of A. So let's go through the indices 0 up to length of A minus 1. And now we're looking at A at J. So if A at J is bigger than or equal to x, and A at J is smaller than A at I is the best one we've found so far, then what do we do?
Switch I.
Yeah. Then we say I equals J. So A at J is something that's bigger than or equal to x, and it's smaller than the best one we found so far, so we said I is equal to J. And of course, at the end of this, we want to return I. Yeah.
Won't you have an error on the first go through because you're trying to take A at I and I is the length of A?
Yep. So we'll have an error on the first time we find an element that's bigger than or equal to x. We'll have an error because we're going to look at A at J and A at I, but that very first time I is equal to the length of A. So how do we fix that? So what is another time that we would, how do we avoid looking at A at I the first time? What's that? Sure, we could do another if, so let's break it.
It doesn't, that's just the 0. It's going to take the first value inside of it and it's going to compare it each time.
Except 0 might not be a valid one because it might not be bigger than or equal to x.
Why not just take the value for last, like go into the array, because if there's something that's more efficient than that one, then it'll go no easier. If it's the last one is the best answer, then it'll retain that.
But what if there's nothing?
What if the array is empty?
Yeah, no, what if everything in the array is smaller than x?
Then we just return A at I.
Then we want to return the length of A, right? So let's just work through this carefully. So we know A at J is bigger than or equal to x. So when do we want to update A at I? Seems, if this is true, then we want to definitely do the update. But is there another thing we should check before that? We're trying to avoid this situation when I is equal to the length of A. So what do we do in that case? Yep.
We just set I to J.
Yeah, we just do the same thing. Because this means this is the first index J where we found something that's bigger than or equal to x. So far it's the best one we found. It's in fact the first one we found. So So this does what we want. So if I is equal to the length of A, we set I equal to J. Else if, so it's not the first value we've seen, we check the value that we've seen, A at I versus the new value, A at J, and update them if A at I or A at J is a better value. Okay. Does that look correct? Yep.
You would still have to filter out if the value, there's no value that's lower than x.
Well, if there's no value that's that is greater than or equal to x,
Lower than
then this never happens. This is never true, right? So if this is never true, I never gets changed, so I is still equal to the length of A by the time we get to the end. Okay. So you can actually write all of this in one line if you want to see that. So let's just test this. Let's say import random. Sure. So let's make an array with a bunch of random numbers in it. Anybody remember how we could do that? I don't know, let's just say n, 2 times n. So we generate a random number, and we want to do that for, I don't know, we just want to count for I in range n. Right. Look good? Okay. And now let's test this a bunch of times. For R in range n, let's say print
What do you have to in the one thing?
because I want to put the value in as well. Well, let's do it a little bit nicer, just so everyone understands. We pick a random number, and we search for it. That was called search in A for x, and now we'll print. Well, if I is less than len of A, z equals A at I. So x, z, I. All right, let's try this. Syntax error. Okay, so this will give us an idea if we did this correctly. So we searched for 1640, we got 1644 as the answer, the index was 625. We searched for 561, we get 562. We searched for 866, we get 866. Search for 1957, we get 1958. This seems to be doing what we want, right? We're always getting a number that's bigger than or equal to the number we're searching for, and we're getting the index of that number. Okay. Anybody want to see the one-line version of this? Anybody care? Yes? All right, let's try it. So we basically have three conditions that we want to check. Basically, if a at j is bigger than or equal to x, and one of these other two conditions should be true. At least one. So, if I is equal to the length of a, or a at j is less than a at I, then we want I equal to j. Now, is this going to work? Yeah, so we should be careful about this. This is a bug down here. So let's put an R there. So that seems to work. Now, why does it work? Yeah.
It's just doing the exact same thing. It's first going, checking to see if that first condition is true.
Yeah.
And then one of the other two has to be true.
Okay, but this condition is the dangerous one to check, right?
Yeah.
So why does this work, and before it wouldn't have? Why does this work the first time we go through? This is a really subtle thing about programming languages, and this Python and C and Java and many programming languages like it, and this particular kind of Boolean logic. So if I ask you, is A or B true? So is I equal to a length of A, or is A at j less than A at I? If this first one is true, do you have to keep going? No. If you take the or of two things, if either one of them is true, then the whole thing is true. And so Python and languages like it do what's called shortcut evaluation of Boolean logic. So when they have an or like this, they evaluate the first part. If that's true, they skip the second part. There's no need to evaluate the second part. You already know that A or B is true if A is true. It doesn't matter what the value of B is in that case. So if I is equal to the length of A, it doesn't bother evaluating this second bit, which is good, because if it tried to evaluate the second part, it would generate an error, but it doesn't. So this is a common trick that gets used in these kinds of things. If you have something that, it's a Boolean, or it's a truth value that you want to check, but there's some cases where you're not allowed to check it, then you embed it in a formula this way that avoids checking it if the dangerous cases occur. And we don't see it here, but there's something else or we don't notice it here, but there's another shortcutting that happens when you have an AND statement. If the first part of it is false, then there's no point evaluating the second part, because false and anything gives you a false value. So that's another tool you can use. Okay. So that's just an aside. I wouldn't say that this is really any more, not significantly more efficient than the other way of doing it. It's just a slightly shorter code. Okay, great. So we can run this code. We've skipped the printing. It runs pretty quickly. Let's try it with 10,000 elements. It's quite slow. So this is an array of length 10,000, and we're doing 10,000 searches. So we can do a little bit of calculations here. So we have n is equal to 10,000. That's the length of our array. And now a search actually goes through the whole array, right? So a search says for j in range length of a, and it goes through the whole array looking for these things. So this means that the number of things that we look at, so we're doing 10,000 searches, each one is looking through an array of length 10,000, which is 100 million. So this takes a while because when we do 10,000 searches on an array of length 10,000, we end up looking over all of those searches. We end up inspecting 100 million elements, and that's that takes some time. It'll finish as it did here, but that'll take a while. Okay, so if you have an application like this, and you find that you have this array or whatever, and you want to do some searching on it, well, like, similar to this, where you're repeatedly searching in this array, then we see that this isn't a good strategy. So even for a fairly small array, only 10,000 elements with 10,000 searches, takes 23 seconds to complete. And so if this is going to happen, then as you suggested, maybe it's worth sorting the array first. Okay. So let's try that. So we can do all this, and let's so we can sort A. So maybe we could use the sorted version of A and this stuff.
It'll take a while though, 'cause it has to sort all the way through A, so then it has to still do the same thing.
Yeah, so where did I? Oh, the sort's in place, yeah. Yeah. I constantly make that mistake. Okay, there's no attribute name copy. Okay, so we make a copy of A. That's this way of doing it. We sort that copy and then we use that instead. That doesn't really help anything because this search routine is still going through and looking for all the elements. How can we make it faster? Using the fact that it's sorted. Yep.
We start a point of x only within A. So we find the first time x appears in A, and then we start searching from there.
Well, if x appears in A, then we have our answer because it's...
So we can just search, because we're sorting too low, we can just go find like the values in between x and then just pick the one above.
Okay, so if we search this way, well, let's just start with what we have. We search through this thing looking for some value to some value that's bigger than or equal to x, and then it's smaller than all these things. So if A is sorted, is there a quick and easy shortcut we can take now?
Index.
What's that?
Index x with the index, and then just keep going through that, and then add 1 until it hits 1, and then that's going to be the first filter answer.
Well, a little more simply. Yeah. We could do index, but let's keep it explicit so that we're actually iterating through it. Because we can't do index x, because if x is not there, index x is going to give us
Well,
minus
we
1.
do
Or,
we do a 4 and then
yeah, but we might as well just do that ourselves since we already have the code for it. But I mean, let's go back and look at this picture. Where'd you go? There. This is our let's say these are the values that are in our array. And now, actually, since the array is sorted, this is A at 0. This is A at 1. This is A at 2. This is A at 3. A at 4, and so on. And the last one is A at len of A minus 1. So we're searching through this thing, looking at A at 0, looking at A at 1, looking at A at 2, and each time we're checking if the value that we found is bigger than or equal to x. So what's a really quick and easy optimization we can do?
look at A at x.
Well, no, not A at x, because x is some number, it's not an index. But, I mean, let's search for x here. A at 0 is not bigger than or equal to x. A at 1 is not bigger than or equal to x. A at 2 is bigger than or equal to x. Should we continue?
No,
Why not?
because everything after that is going to be bigger than a.
Yeah, because the array is sorted, everything after A at 2 is bigger than or equal to A at 2. So this is actually the smallest one. This is the one we're looking for. So this code can be simplified to just this point, return J. And we don't need this anymore. So the code gets a lot simpler, and the first time we find something that's bigger than or equal to x, we know because we're starting at the smallest values and only increasing that that's the one we're looking for. And if we don't find, so we return it. If we don't find anything, then we'll just return the length of A. Okay. So let's see if that's any faster. Still not terribly fast.
So we have to sort all the way through A.
Let's see how much faster it is. Well, it doesn't have to search all the way through A, right? It gets to stop.
Well, it has to sort A first, though.
It has to sort A first,
Which is what it is.
but yeah. So it has to sort A, which takes a while. But if we look at the total time here, it's actually gone down quite a bit. So before it was 23 seconds, now it's 5.8. And so where's the savings?
That extra chunk that we did that's not going after J.
Yeah. So as soon as we find the value we're looking for, we get to stop. And we can usually find, in this example, the value we're looking for. We usually find it after looking only through about half of the array. And so that shaves off a good chunk of time. So in fact, it shaves off more than I expected. So let's, if we do this without using this optimization, it takes quite a bit longer. We're looking at probably 20 seconds or so, which was what we got last time. Yeah, so 22 seconds. So already just that little trick saves a lot. But what can we do to really speed things up if we want to search a sorted array? I know you guys know this because you've given me the answer before. At some point in this class we played a game. Yep.
Guess the middle.
What's that?
You guess the middle number, and then depending on if the x is above it or below it, you guess the next middle, and you keep cutting it down to half.
Yeah. So one of the first games, actually, when we were looking at while loops, one of the first things we wrote was a silly guessing game where the program picks a number between, I don't know, 1 and 1,000, and then you guess it, and it tells you if you guess higher or lower. And people in this class already knew how to play this, how to beat this game, which was you first guess 500, and then it says higher or lower, and then you know that it's somewhere between 500 and 1,000, or you know that it's between 1 and 500, and so each time you know it's in some range, and you guess halfway in between. Well, searching a sorted array is exactly the same thing as that guessing game. So you're searching for the index of this particular element, which is greater than or equal to x, and it's the smallest such one. And well, you guess that index. So you'll say, I'll guess that it's halfway through the array. And then if you look at what's halfway through the array, you'll know whether your guess is too big or too small, right? You can compare that to the value x that you're looking for and know whether it's too big or too small. So how do we do that in code?
Last index plus the first index over 2. Well, yeah. It's the index number, the amount, not the actual index value.
Yeah, okay. So let's we're going to imagine we're going to do our side of this guessing game. So initially we know very little. Yep.
You can do the length of a integer division by 2, and then that's our starting point.
Yeah. So let's set it up in a general way, so that's just one special case of the general thing. So we'll know that initially the thing we're looking for is somewhere between index 0, or it's above index 0, and the number of the length, or the number of elements that we're looking at, is equal to the length of A. Okay. So we'll continue, and when should we stop?
What, guessing turning points? Or
Well, at some point we want to stop, so we'll figure that out. Somehow when we know the answer, when there's no more options, we'll maybe stop.
Didn't you say there was a number that there's no more you can do it with when you're doing the guessing game? It was like 7?
Yeah, but sometimes we'll stop before that, so we'll figure this out later. So our guess, G, was, a few of you have said it, we want to start at our low index, initially is 0, and then take n divided by 2. So initially this is just going to be n divided by 2. All right, so we're going to look at A at this guess. And what cases should we worry about?
Whether it's bigger than x or smaller than x.
Okay, so let's see. There's sort of two kinds of elements. There's those that are bigger than or equal to x, and those that are smaller than x. So if A at G is bigger than or equal to x. Yep.
Shouldn't we not be using equal to because it's equal to we have the answer?
that doesn't matter. There might be more that are equal to or whatever. We won't worry about that for now. We'll just see what happens when we do it this way. So if the element we're looking for is bigger than or equal to x, what does that tell us? Let's draw a picture of this. So we have all these elements. We just picked one. This one here. This is a at g, our guess. And this number is bigger than or equal to x. So that means that x is somewhere over here on this side of the line, including possibly equal to this number. So where should we continue searching?
From 0 to wherever that point is.
From low, so g in this case is 3, 0, 1, 2, 3. So we want to search from 0 up to 3, right? So we won't change low. Instead, what we'll do is change n and have that equal to, is it g or g plus 1? I see 4 elements here, and g is 3. So it looks like maybe it's g plus 1. Yeah? Right, if initially n is the length of A.
Yeah, so it's 2 plus 1.
Yeah, okay. Let's try that. Otherwise, if that's not true, then that means x is over here on this side. So x is actually bigger than g, or bigger than a at g. So where should we continue searching?
You change the low.
Yeah. So this was our low before. Now we want to change it so that this is where we search. So we know the answer is not g, right? Because g is not actually big enough. So we can set low to be g plus 1. Okay. And great, so far so good. Is that all we have to do? Yeah. So it's not only when we change low, right? Initially we had n, low is equal to 0, and n is equal to 1, 2, 3, 4, 5, 6, 7, 8. But now we've just changed low so that low is actually 4, and now we have 1, 2, 3, 4 elements that we're interested in. So we want to set n also equal to 4, or more precisely, n equals n minus low. Okay. And all right. So eventually we're done. What do we return? Low? Low plus n?
It would be, we have to wait to return. Because we have to wait until it's either equals x.
Yeah, we wait till the while loop is over. So maybe that's what we should think about. When is this while loop over?
When it equals x or x plus 1.
Well, not x plus 1, it's just some number bigger than x, right? But what's getting smaller every time this loop executes? N. So just like when we played the guessing game, there's a point when actually we don't have to guess. We don't even have to ask the computer. We know the answer. And, well, what is that? Do we know the answer if n equals 1? If there's only one element in the array?
Yeah.
Yes?
No.
No?
Pretty small.
If n equals 1, there's still two possible outcomes, right? The thing is smaller than the element or it's bigger than the element. So we actually only know the answer once n equals 0. So hopefully we'll actually get to n equals 0. Maybe this is an infinite loop. Who knows?
Doesn't it have to be true to keep looping?
What's that?
Doesn't it have to be true to keep looping? So wouldn't you have to say not n equals 0?
Oh, sorry, yeah. While n is, you're right. While n is bigger than 0. And then we'll return low. So if n is 0, then well, then we return low, which is where this thing last stopped. All right. So we better test this one. Seems unlikely that it'll actually work. Say x.
Oh, yeah, it's true.
Okay, if a at g is bigger than or equal to x. So we get an index error here. Anybody guess why? Well, the index error is coming here, right? List index out of range.
The line should be -1.
What's that?
It should be at -1. Divided by 2.
Well, let's take a look and see what's happening. Let's trace it out and see what values g is taking. So it starts at 50, then goes to 75, 89, 96, 99, and gets to 101. And our n is 100, so it's actually quite a bit bigger. So I'm surprised that that's so. It immediately goes off the end like that, but okay. Let's print everything and see what's happening. So this time we get an infinite loop. Okay, let's see. So there's our array. It has values up to 198. And we started at 50 and climbed up to 101. So let's see. Why that was the case. So this is just evidence for you guys that binary search, even though it's actually very easy to describe, you almost always get a bug when you implement it. So, any guesses where the problem is? I need your help.
You can make n len minus 1.
Okay, we can try that. Not sure that that's going to do it. Maybe it will. No, still goes up to index 100 in that case.
Take the +1 off G.
In which part?
That one.
This one?
Yeah.
Let's see. Now we're stuck. Is it?
Remove the -1 off the len.
Remove the -1 off the len.
There you go.
No, still an error. No ideas? Well, let's keep debugging. Let's print. This way. A at low up to low plus n.
The problem is it's not rounding.
Difficult to say what's happening. Let's go with a really short array. One of length 10. Okay. So we start with an array of length 10. What are we printing? A at, well, printing A and X. This is the value, this is A, this is X. First time through the loop, this is the range we're looking at. Second time through the loop, we're looking at 0 through 7. Is that correct? Yes, because we're searching for 3, so we picked the correct half. Next, we're looking at 0 and 4. Is that correct? Yes. Next, we're looking at 0 only. Is that correct?
No.
No. So, where did that happen?
We divided it by 2.
So what was G in that case? So if the length, if n is 2, then what is G?
G is going to be low +1.
So the length is 2. We divide that by 2. We get 1. So we're comparing x to 4. Right? X is 3. So x is less than or equal to 4. And now we say n is equal to G. So, okay. Is that correct?
So we need another statement.
Well, I don't know. Do we? So at this point,
With the len of
I think we should be able to do it without an if statement. We just need to get things right. So if x is less than or equal to a at g, so a at g is potentially an answer. In this case, x is 3. It's less than or equal to a at 1. So what should we...
And the length of it isn't 2.
Yeah, so somehow the problem here is this n divided by 2 thing. Somehow giving us a wrong answer. Although, yeah, I'm not... What's that? No, I didn't, but I'm only using integer division, so there's no question about it. No? All of us can't debug this?
And G isn't equal to 2.
The only thing I can think of is if you put else if it's more is above.
And then have a special thing for G for n equals 2 or 3 or 4. Yeah, it's not really what I would like. So at this point, it decides it's going to search on this array. Now, is that the right thing to do? Actually, it's not the wrong thing to do, is it? Because on this array, I'm searching for 3. And what's the return value?
0.
No, because 0 is what? It's less than 3. So there's nothing in this array that's bigger than or equal to 3. So I should return 1, which is actually the right thing. Okay, so that actually seems to have done the right thing up until there. Now something really strange happens. We get the return value is wrong. So this actually ran correctly. It gave the index 1 and said 3 maps to 5. Oh, I know what that is. Shouldn't get that wrong. So here's where we have a real clear problem. We're searching for 7. First thing we do is compare that to something. G, the halfway mark in this array. We get this part of the array. Next thing we do is compare it to, I guess it's 5. We get this part of the array. And now something really weird happens. We're searching in the array that has 6 and 9, and it gets bigger. So there's something really broken with the code. Where could this get bigger?
One integer division by 2.
I see the problem.
So
Yeah, I see the issue here. So G is an index into the whole array. Low then gets reset to G plus 1. It's an index into the whole array. And this is the problem right here. This thing is not, this is some value n which could be really small. I mean, n could be 1 or 2, and we're subtracting an index that's as big as the whole array, potentially. So we should fix that. So how many elements do we lose from the array when we set low equal to G plus 1?
Everything from low to G plus 1.
Yeah. So when we do this, when we go from, let's say, this is low, this is G, this is G plus 1, let's say 0, 1, 2, 3, 4, 5, 7. So here we have an array with 8 elements, and we take low and we move it all the way over here. How many elements do we have left? 4. 1, 2, 3, 4. And so what is that? If you express that as low in terms of low and G. This number here, right? These are the elements we lose, which is G minus low plus 1. See if that helps. Now we've changed a few other things which I'm not convinced was the right thing to do since then, but we'll see.
Just seems weird using like low and G plus and over to. Why not just use the 10 values on the exam?
Why not just use,
Wouldn't that make it a little easier? Like beginning and ending index?
okay, so yeah, I mean we can try and use this with beginning and ending index. I mean both are possible, but so now we have this one issue that's occurring right at the ends of these searches. Well, actually not even right at the ends. So here we have an example of it growing again. Okay. So I'm not going to be able to, probably not going to be able to debug this right now. We've spent enough time on this. Well, not on the implementation bugs. What I really like to talk about is what we gain here in terms of efficiency, assuming we get something working. So let's go back to our example of 10,000 elements, and we're doing linear search on an unsorted array. So we end up looking at 10,000 by 10,000 is 100 million entries. So that was just linear search. We had another version of this, which we had an array. We were going to do 10,000 searches. So this is the number of searches. And this is the number of elements that we look at in each search. So once we switched to a sorted array, we got to use this search sorted. And so what did we save there roughly in terms of number of elements we have to look at before we find what we're looking for? Depends on how big X is. So in our sample code, the elements in the array were random, and so was the choice of X, the element we're searching for. So about how far through the array do we have to go through before we find what we're looking for? Yeah, to X. So on average, how far would that be? And pick a random, if I pick a random index between 1 and 10,000, on average, how big is that index? Or between 0 and 9,999. Just guess. Pick a number between 1 and 10. What's the average number that comes up? Yeah, 5, right? So somewhere in the middle. So since I'm doing this search and I'm stopping the first time I find something bigger than x, well, everything in the array is random and x is random. So I expect sometimes I'll find it near the beginning, sometimes I'll have to go all the way to the end. But on average, I'll find it about halfway through. So on each search, I'll only have to look at about 5,000 elements. So that speeds things up. So instead of doing 100 million inspections, I'll only do 50 million inspections. And actually the timing results we got were better than this. They went from 22 seconds down to 5.5. So there's some other things creeping into that. But, I mean, definite improvement there. Now what we're trying to implement, which we were not successful in, is binary search. So we're still going to do 10,000 searches. Now how many elements do we have to look at during each search? If we do binary search, so our first guess is going to be 5,000. And then our second guess will be well, something that reduces the number of elements. So after our first guess, we only have 5,000 elements to worry about. After our second guess, we only have 2,500. After our third guess, we only have 1,250. And so how many guesses do we have to make? So does anybody know? So has anybody taken a calculus course? Yeah. Learn about any special functions in calculus?
Logarithms?
Logarithms. So what's a logarithm?
The inverse of an exponential.
The inverse of an exponential. So
times x log 10,000.
So 2 to the x is equal to 10,000. Right. So that's basically what we have, which is the same thing as x is equal to log base 2 of 10,000. And the nice way to think about so exponentials basically say take some number and multiply it by itself x times. That number is called the base. And logarithms say take some number, 10,000, and keep dividing it by some other number, 2. And how many times do you have to do that division in order to, before the number you have gets smaller than or equal to 1? It's basically what this tells you. So the easy way to do binary logarithms is to memorize all the powers of 2. No, not so much.
Do 4 log 2 to the third. So
13, 14. Well, I'd say 14.
So let's see.
14 gives you 16,000 something. And
Yes.
13 gives you 8,000 something.
Yeah. So 13.2 is the average, or it'll be 14 in the worst case. Okay. So it's not 10,000 elements that we have to look at. It's not 5,000 elements that we have to look at. It's 13 elements. So we're going to have 130,000. So, well, this was 100 million. This was 50 million. So to even get in the same ballpark as these things, we have to basically take off 3 zeros here. So this is going to be something like, 500 to 1,000 times faster than either of these other two searches. And I'll finish this up. I'll finish this code up when we get back, and when I get back to my office, and we'll look at it again. But this shows you that really by, doing the right thing, doing things the right way, you'll have the difference between if 5.5 is 50 million, then what's 130,000? It's going to be a fraction of a second, right? So we'll come back to this next class.